Alright guys, so welcome back. Last time, all I did was talk a little bit about topology and a little bit about metric spaces and compactness, just really quickly as a review, and kind of just gave an intuitive way to think about dynamical systems. So today we're really going to get into actual dynamics and get into some definitions on maybe what a dynamical system is, and maybe talk about a few examples. Okay, so let's start right off the bat. So the definition of a dynamical system. So here we have a dynamical system, and we're going to write it as a pair. So we're going to have a space M, we're going to have a map phi. Just consists of a compact metric space along with just a continuous map. And that map should be from, it's going to be fine. It's going to just take M into itself. Okay, so that's, in general, this is kind of all we're really assuming about our system. The compact metric is really just for convenience. It doesn't have to be compact, doesn't even have to be metric. It could just be topological space. Yeah, Eric?
Does it have to be a measure preserving map?
Not at all. No.
Okay.
This isn't like a measure preserving system like in some classical maybe dynamics that's usually done. And we're really not going to refer to the measure at all with this. We're just going to talk about kind of like compact metric space, some topological things we could talk about, maybe just the orbits and periodic points and stuff like this. Okay, so nothing as far as measures concerned. So, like I said, it doesn't have to be metric, it doesn't have to be compact either. It just really has to be a topological space so that we can put continuity with it. And continuity is kind of a, I mean, if you want to take everything off of there, I mean, it would be kind of hard to do any dynamics with that, but this is what we're dealing with here. So, this kind of notion here where the map and the space, so essentially the space is just a compact metric space, and then the map itself is just continuous. If that's all you really assume with that, we're kind of in the realm of something called topological dynamics, because we can really only talk about topological things with this. So the notion above, where phi is only continuous, is really known as a topological dynamical system, or really what I'm going to call it. So it's essentially a topological system. That's really all we can discuss with that. If you add any other, conditions to phi, like let's say that you can talk about differentiability in the sense that maybe you're on a manifold or anything like that. I won't talk about the manifold too much, but you can talk about derivatives. We're going to go into the category of smooth dynamics instead, if we can talk about derivatives. Okay, so if M has some kind of has a smooth structure to it, so that we can put some kind of regularity condition on phi. Then this is really just a smooth dynamical system. And we could really put anything we want as far as differentiability is concerned. We could say maybe phi is C1, C2, C infinity, doesn't really matter. It could even go into things like Lipschitz as well. Okay, so this really falls into the realm of smooth dynamical systems. And then finally, since Francois had talked a little bit about stochastic differential equations, if you allow a little bit of randomness in your system, dynamics does tackle this as well, and it's called random dynamics. So, so if our system is allowed to exhibit random behavior, and I'll kind of put that in quotes, since I'm not going to really kind of describe a lot of these. So if it's allowed to exhibit any kind of random behavior, And this would be called a random dynamical system. So these are just some of the examples of some additional structure that you can ask for as far as your map's concerned, just depending on what kind of system you're dealing with and what your system is kind of showing in that. So what we're going to do is we're going to talk, I'm really going to kind of stick to the unit circle as kind of the examples. The examples on the unit circle, the two that I have are pretty easy, but they really drive the point home, and they can really show you how things are really, really delicate as far as dynamics are concerned. Okay, so the first thing that we're going to do, which is really noted in the definition as well. So since we're kind of going to be dealing with the unit circle, and remember the last time that we'd done the unit circle is that we viewed the unit circle we really view this as the unit interval, which is 0, 1, with the points 0 and 1 identified with each other glued together. Okay, so we're really viewing S1 as this thing, really in the unit circle, in the unit interval case where the endpoints are glued together. Okay, so I'm going to use, some of the maps are going to have this thing where the map will be defined and then I'll put a mod 1 after that. Okay, so let me define what that mod 1 actually means. Okay, so for one thing, just know that each R and R can be written uniquely as R is equal to n plus S, where n is some integer, and S is some number between 0 and 1. Okay, so we can break down any real number into kind of its integer part and its fraction part. That's really all we're doing here. Okay, so by writing it like this, bless you, if we write it like this, then we write so in this case, we're going to write that R, this can grow into S, and then mod 1. So this is very similar to the kind of modular addition from algebra. Okay, so since we're doing it with the fractional part, S is going to be some kind of fraction in between 0 and 1. We're going to write this mod as here. Okay, so it's really kind of equivalence costs if you want to think that we're dealing with, but we're really only going to care about the S part. That's going to kind of give us, this mod 1 is going to give us all, it's going to keep getting us right back into the interval 0, 1 whenever we do this kind of modular addition. Okay, so the mod kind of works like the mod does in algebra. Okay, it'll just kind of keep us all inside the unit circle here. And what we do is we call S the fractional part of R. Okay, so I mean, you can take it just an easy example like the number 7.45. You can break it down as 7 and then plus 0.45. So we were really kind of identifying 7.45 with kind of its fractional part by doing this modular thing here. Okay, so the fractional part is kind of what we're going to consider whenever we're dealing with the unit circle. Okay, so let's kind of start getting into. Let me introduce the two maps we're going to talk about some dynamical system things that we tend to look at, like periodic points and stuff like that, and then we'll actually talk about these maps again. So the first example what we have is we're going to let M be equal to S1, and again, kind of think about that identification that we have there as far as it's concerned. So where we view S1 as we have in the note above. Okay, so for a fixed alpha, which can be between 0 and 1. Okay. We're going to define phi of alpha, which is going to take us from the unit circle back into itself. We're going to define that by, we take a point on the unit circle, and we're going to add alpha to it, and And then we're going to attach the mod 1 just to kind of throw it right back into the 0, 1 interval. Okay, so all we're doing is we're adding alpha, and then we're modding by 1. Okay. Another way that you can view this map, this kind of, the way we write this map out is kind of an additive way to write this map out, but there's an equivalent multiplicative way, if you rather think about it like that. And it's good to kind of think of these maps in different ways too, because the proofs of some things maybe, it could be easier maybe to see in the multiplicative way than in the additive way. Okay, so you can equivalently write phi of alpha just goes from S1 to S1. By you take phi alpha of x, and you keep the x, but you have this 2 pi I alpha, like this multiplicative notation. So in either notation that you see, really all this map is doing is that it's taking your point and it's rotating it. It's rotating it by an angle of 2 pi alpha radians. Okay, so for that reason, since this is really just a circle rotation, this is a rotation on the circle by 2 pi alpha, we call this the circle rotation. So this map is called the circle rotation. So this is one of the examples that we'll deal with. And as you'll see in the example, even though the dynamics here, all we're really doing is kind of rotating. That's all the map is doing. What may be a little bit surprising is that how we rotate, or what that alpha is, really makes a difference on what type of things like periodic points and all this stuff pops out. So that actually makes a huge difference whenever we're kind of looking at our dynamics from that point of view. Okay, so that's the first kind of one that we're going to deal with. The second thing that we'll deal with, or the second type of map, so this will be example 1. Example 2. So again, we're on M is going to be equal to S1. And this time we're just going to we're going to define, okay, phi is still going to go from S1 to S1. And this time we're going to define it by phi of x. We're going to do 2x mod 1. Okay, so we're going to double it, and then we're going to mod 1 to get it back into 0, 1. Okay, so again, we're thinking of S1 as the unit interval with the points identified, and this is our map that we're going to deal with here. Okay, so 2x mod 1. So there's a couple of ways that you can think about this map. So the one thing that you do want to be careful of is that this map here, kind of another kind of equivalent way to write this, is that all phi does, remember, whenever you're modding by 1, whenever you reach 1, and since 1 and 0 are identified on the circle, you're really going back to 0. So you're really going kind of back to the beginning of the circle, if you want to think of it like this. So whenever x hits 1/2, it really jumps back to 0. And so this really looks like a piecewise function. So whenever x is between 0 and 1/2, it's just the 2x. And then whenever it does reach 1/2, it should go back to 0. So it'll be redefined as 2x minus 1. And then from 1/2 to 1. Okay, so this is another way that you can see this. Okay. And again, just be careful about the identifications here that we're doing. So again, we're working on S1. So it looks like, especially where the function's jumping from 1/2, where it breaks off from 1/2 to the first piece to the second, that there's a discontinuity there. But since we're on the unit circle, that discontinuity is actually not a discontinuity. So this actually is legit as far as the dynamical system is concerned, as far as this being a continuous map. Because at 1/2, this is going to be 1. But remember, on the unit circle, 1 and 0 are the same thing. Right? And at 1/2 on this one, this is also 0. So from the left and the right, we're really hitting the same point. Okay, so just be very careful of that. This is kind of like what it would look out maybe if you just graphed it on the coordinate plane. Right? So that's one. So these are kind of two ways that you can see this. Okay? And notice also that really this map, all it's doing is it's taking each interval, or the 0, 1/2 interval, and it's mapping it onto the entire circle bijectively. Okay, so in a 1-to-1 and 1-to fashion. So this map feed actually takes 0 to 1/2 and 1/2 to 1 to all of S1. And it does it bijectively. And for that reason, this, and especially with the 2 there, this map's called the doubling map. So this is called the doubling map on the circle. So the 2 key examples we're going to deal with here, the circle rotation and the doubling map. Right now, there's actually a very nice way that will probably not be as obvious for this, that you could also view this map. Okay, and this is going to tie into hopefully some of the symbolic dynamics that I'll get into as well. Right, so we'll clear off a little bit of room here. So let's do an alternative view of the doubling map. All right, so for each, since we're only dealing in essentially the interval 0 to 1, so for each x in 0, 1, what we can do is we can just rewrite x in its binary notation, essentially. So we can associate it with a binary sequence. Okay, so for each x in 0, 1, we can associate a sequence. We're going to write the sequence out as x0, x1, x2, dot, dot, dot. We just keep going on forever of zeros and ones. Okay, so that we can just write x as an infinite sum where the sequence is going to be involved in that. So we got n equal to 0 to infinity. We do xn over 2 to the n plus 1. Okay, so this is for everything in 0, 1. And so we can write our number alternatively in this kind of binary notation. All right, so this is just the familiar binary 2 expansion of this number. Okay, so what's going to happen whenever we apply that doubling map to that? So if x has nothing but as a binary representation or binary sequence associated to its x0, x1, x2, dot, dot, dot. Whenever we apply that map to it, with phi of x, well, that's just defined as 2x mod 1. And this is just going to be the sum from n equals 0 to infinity. Okay, we're just multiplying the top one by 2. So 2xn over 2 to the n plus 1. Okay, so the first term whenever we take the n0 term, okay, all we're getting is just that x0 to pop out. Right? And then we can shift the term right back and start it off there and still end up with this as that. So we're essentially picking out the first term of the sequence, okay, which is just going to turn into x0. And of course, if I don't write it, I'm going to forget it. I know I will. So the mod 1 is still there. Okay, so here, remember that this x0 here, x0 is a sequence of zeros and ones. So if x0 is 0, well, who cares? It's not really there. If x0 is 1, remember we're mod 1ing. We're in mod 1 addition. So adding 1 or adding an integer in mod 1 addition doesn't change anything. So we can just drop this down, and all we're really getting, okay, is the sum from, oops, sorry, I forgot, this should actually be n plus 1. Okay, so this would be x to the n plus 1 over to the n plus 1. And what that's going to do is, we essentially had the sequence before where we were representing it x0, x1, x2, and then our sum kind of starts like this. This is just shifting the sequence. That's all it's doing. So this is the binary representation. This is just the representation using the sequence x1, x2, x3, and so on and so forth. So really the action, if you think about it in binary form, the action that 2x mod 1 is doing is that it's taking your binary sequence and it's shifting it to the left and killing the first term. That's all it's doing. Okay? This is usually really, really helpful. If you have this kind of coding that you can do, and your dynamical system really is just a kind of a shift here, it can make a lot of the things that you want to prove about periodic properties and all that stuff really, really easy to deal with. And it makes it a lot easier to take care of. Are there any questions on any of those two things? So those are the two main examples that we'll essentially be dealing with. Yeah.
We want to pull out the real part of that complex exponential, right?
What's that? Sorry?
Your e to the 2 pi I alpha.
I want to pull out the...
Just the real part.
Wait, why? Wait.
Never mind.
You good? I think this is fine, right? Yeah. Okay, so right now, the two examples that we're dealing with are just dealing with one dynamical system. So let's say our dynamical system is described either by the doubling map or the rotation here. So what kind of questions can we answer about this thing? So let's kind of define a few key terms and then let's talk about these maps.
I have a question about your binary sequence. Sorry, so if you have a x that's rational and it's non-repeating,
Yep.
then the kind of, like the orbit is not, you can know all the places it goes, but at some point you're going to have that, like there's going to be some xm for which it's all 0 after that, right?
Right.
So then you kind of like lose information in a sense. Because say like 3/4, right? Which
Yeah.
is like 1, 1.
Yeah.
0, 0, 0, 0, 0. So like actually that point, if you iterated the map over and over again, would keep going through the interval over and over again.
Yeah, it kind of tells you by kind of by viewing it right here, the doubling map has a fixed point, right? It has a fixed point at 0. So by viewing it as a sequence, you can kind of see what points are going to go towards the fixed point, like which ones are going to kind of converge over there as well. So what, like even if, like what are you losing though?
I guess I'm wondering, like, can you determine what the period is from this sequence?
Absolutely, yes.
Okay, you're going to tell us how?
And this is what we're going to do, right? So I'm going to define what a periodic orbit is and all this stuff, and I'll determine how you can figure out the period. And in fact, you can construct very easily, based on the sequence, you can construct periodic orbits of any length that you want very easily. Just by noticing that this thing just shifts your sequences down to the left. And you're really not losing that much information because your example of 3/4. I mean, if you apply it just without doing the binary representation, if you keep applying this map, that's essentially going to go to 0 anyway.
Oh, duh,
Right.
sorry, that's why. Okay,
You're really not
thank
losing
you.
anything.
No, just my understanding of rational numbers, that's all. Okay.
That's all good. So, so let's talk about some of these things. So I've been kind of throwing these words around, orbit and all that stuff, so let's officially define them. So for a dynamical system, if I don't say anything, of course, about the dynamical system, M is compact metric and phi is continuous. That's all we really need for this stuff. So the orbit of a point of a point x and M is just the set of iterates. Just the set of iterates as we apply phi over and over and over, and we're going to let it go to infinity, kind of see kind of look at this thing asymptotically. And we do, the n equal 1 to infinity is going forward in time, so this is the forward orbit, if you want to think of it like that. Right? So we'll define it like this if phi is not invertible. So of course phi doesn't have to be invertible a priori. It could just be a continuous map. And then we can actually go backwards in time if it is invertible. Now technically, I mean, if your map is not invertible, I mean, doing phi to the -1 and viewing it as a pre-image still makes sense. It's just that you may have a choice to make as far as that is concerned because it's not bijective. If it's not invertible, it's not going to be bijective, so that pre-image may give you multiple points. So you could have some problems as far as being well defined, and it could matter which point you decide to take. Right? So just be careful of that too. So we just talk about the forward orbit if it's not invertible. Right, and then another definition here. Now we'll talk about what type of properties maybe can this orbit have. So same setting. M phi is a dynamical system. So a fixed point of phi is a point x and m such that the dynamics doesn't do anything to it. So phi of x is just equal to x. Okay, so it's a point that's essentially not changing. Nothing's happening here. Yes?
So for the first definition,
Yeah.
are you restricting the countable sense or finite sense?
Yeah, I'm restricting. I mean, this is going to be countable, right? So we're letting go to infinity. Oh yeah, I want to make this thing. So I'm just dealing in kind of the discrete case where you're just doing n equal 1, 2, and all that stuff. There's nothing stopping you from redefining and doing like over R or anything like that, and doing a flow instead. So you can do this, of course, in differential equations, or really with anything. All right, so a fixed point of phi is a point x and m such that phi of x equal to x. And just as a side note, you also get that no matter what iterate you're on, no matter what orbit point you're on too, nothing's going to change. So you can keep iterating that point, but nothing's going to happen there. And a periodic point is a point x and m such that phi n of x is equal to x for some n in the natural numbers. So it's essentially a fixed point of the map phi n, if you want to think of it like that. All right, as you iterate, you're essentially going to get right back to where you started from. So you kind of have some circular behavior going on there. The definition itself doesn't say anything about the minimality of n, but just to refer to the period of a point here, the smallest n for which that's true is going to be called the period. I guess that's what it's called. So the smallest n, smallest such n is going to be called the period. And if
greater than 0, right?
what's that? I'm sorry.
And greater than 0. Right?
Yeah. The natural is using the convention that it starts at 1 and goes to infinity. I know other people don't maybe start at 0, but yeah, it's going to be from 1 to infinity, of course. Okay, so if this orbit that we're looking at, that x happens to be a periodic point, then we'll refer to that as a periodic orbit, okay, for obvious reasons. And then the last thing is that a point can be periodic. In other words, it'll kind of start right back where it'll kind of end, if you will, right back where it started from. We also have a notion of something that's eventually periodic. So it can eventually become periodic, but it doesn't show any periodic behavior kind of right at first. So an eventually periodic orbit, write this on top. So an eventually periodic orbit is a point X and M. Such that for some positive integer, j greater than 0, so we have that j x is a periodic point. So all it's saying is that you just have to go through the orbit kind of j steps, and then at the j step, then your orbit's going to start giving some periodic motion. So essentially, if you want kind of a picture on what's going on there, it's kind of your starting point. It's going to be phi1, and then if you travel and keep going, and then you end up with phi j, and this is whenever you start getting kind of periodic behavior, and things are going to start kind of wrapping around and getting back to there. Okay, so essentially all that means, if you want kind of the mathematical terms for that, if the phi of j is a periodic point, then that means there exists some n greater than 0, such that phi of j plus n will get you right back to phi j of x. So it's periodic kind of down the road. All right, so are there any questions about the definitions? These are the main things that we'll kind of talk about. Okay, so what kind of things can you ask about a dynamical system? So what things are we really interested as far as a dynamical system is concerned? So we're going to be interested in fixed points, of course. We're going to be interested in what the orbit looks like. We're going to be interested in periodic points. Really, the one key thing we're going to kind of be interested in periodic points is how many of them are they? Are they dense in some kind of way? What's going on with this? And so let's kind of catalog all those things. So what are some typical questions that you can ask? About m comma theta. I'm sorry, m comma theta. So number one, so for each x and m, are there periodic points close to x?
So how are we defining close?
This is very like, all right, so we're in a metric space, so closeness makes sense,
That's
right?
sufficient.
So yeah, so we're dealing in a metric space here, so it makes sense to ask about density. Of course, in here, I mean, it makes sense to talk about density in other places too, but as far as here, close, since we have a metric, it's going to be in terms of the metric. So for each x and m, are there periodic points that are close to x? So how dense are the periodic points? Number two. You can ask kind of a probabilistic type of question. How are the points? How are the points of an orbit distributed? The iterates kind of staying close together? Are they going far and wide all over the set? Who knows? These are some typical things that we want to know. So the third one, given a subset U of m, how do the sets, instead of taking instead of taking orbits of points, let's say we can take an orbit of that set and how that set acts under the dynamics. How does this set spread? Throughout M, as we let n go to infinity. Okay, so what's happening to those sets? Are those sets kind of seeing, or if we take some other set like V, is this set eventually going to come into contact with that after a certain number of iterates? Okay, so is this set being kind of spread all over the system, or is it kind of staying in one general area as well? So in particular, if U is open, and V is another open set, so does there exist an N such that phi n of U, if we intersect that with V, and we get something that's not empty? Does this happen? And then just one really quickly, what's happening by the fixed point? Are they attracting, repelling? Neither? What's going on with that? So what are happening near fixed points? What is happening? So these are the 4 questions that these are some of the questions. Of course, you could ask a ton more. Okay, there's just a few of them on what you could ask, and then we can at least tackle some of these in some of these examples that we're doing before for the circle rotation. Okay, so a lot of the questions kind of deal with the spread, or how things kind of spread throughout, or what the dynamics are doing with that, and a lot of periodicity too. Okay, so these are kind of the main questions that we're going to deal with. All right, so let's get into these examples. All right, and what the 2 examples will show you is that the x that we start off with, or you can think of that as the initial condition. Some maps are very chaotic. You change the initial condition a little bit, you get completely different dynamical behavior. The first one that will show about the circle rotations, that if you change something really small about the map, you can also get really different dynamical behavior. So the first example we're going to do is the circle rotation. So we're going to do phi alpha of x. Of course, just to remind you, is going to be x plus alpha mod 1. You want to view it kind of in the additive way, or you could also view it as phi alpha x with x e to the 2 pi I alpha. Either way. All right, so remember alpha. Alpha is just any number between 0 and 1, including 0. So let's just get rid of the easy case first. And so if alpha is 0, well, nothing's happening. Everything's fixed. So it's the identity map. Identity map. Everything is fixed. Nothing changes. So nothing interesting really happens here. So kind of get that case thrown out. So let's now just take an alpha that's between 0 and 1, not including the 0 now. All right, so we have 2 cases that we're going to consider. We can consider the 2 cases where we kind of have different behavior is if alpha is rational and if alpha is irrational. These are our 2 different cases. So case 1. Say alpha is rational, and we'll write alpha equal to m over n in its reduced form. So let's talk about periodicity here, okay, about the periodic points. Okay, remember that alpha, you're just rotating through an angle of 2 pi I alpha. So if you're rational, what's going to end up happening as far as periodicity is concerned, every single point is periodic. Every single one of them. Okay? And that can be seen just as, just because that thing is rational. Okay? You can actually prove that the only way you're going to get periodic points in this kind of system if alpha is irrational. Okay? And you can use it using either that or that as well. So in this case, every point is periodic. So we get periodic behavior just really everywhere as far as this system is concerned. And in particular, depending on what this alpha is, if it's in reduced form and that denominator is n, every point is periodic with a period of n. And that's its least period. So every point is periodic with period n. And that's pretty much all you can say about the rational case. Everything's periodic. What else, what else can we really say? All right, case 2, if it's irrational. Okay, so we have, in the first case, alpha is rational, we get periodic behavior. If alpha is irrational, we get absolutely no periodic behavior whatsoever. Okay, there are no periodic points at all. There are no periodic points. And again, you can prove that just by, you can assume that there are, use the either way of the map there, and you'll get a contradiction on the irrationality of alpha. Okay, there are no periodic points, however, what we do get is that every orbit is dense in our dynamics here. And in particular, yeah, I won't talk too much about ergodic, but yeah, you do get an ergodic system for the irrational rotation. For every pair of non-empty open sets, U and V, there exists an N such that, so what you get is essentially, what condition is this? Number 3 here. Okay, you actually do get that. So particularly for every pair of non-empty open sets, U and V, there exists an N such that phi of N of U, you intersect that with V, and you actually get something that's non-trivial. So the circle is kind of will take every open set, it'll rotate it eventually to hit every other open set in there. Okay, so these are kind of the main things here. As far as every orbit being dense in S1, again, you can prove that in a few steps by using either one of the maps there. Okay? And actually, it suffices just to prove, if you do want to prove that, you don't have to prove that every single orbit is there. It actually suffices just to prove that the orbit of 0 is dense in this thing. Okay? Because this map here, whenever you apply this map, no matter what you're looking at here, by adding alpha is really just rotating the point 0 by alpha. Okay? So you really only have to show that the orbit of 0 is dense in there, so you can reduce your problem at least to that. Since every map can be written in terms of x plus some orbit of 0. All right, so this is an example of something that can give you different behavior just by changing the map a little bit. And I mean, we're changing the map from rational, this is dense. And of course, I mean, alpha being irrational, that's also dense as well. But there, kind of in a topological sense, there's a lot of places where you get periodic behavior. If you think more in a measure theory way, there's a lot of places where we get no periodic behavior. So this point of view, whether you like to take a topological type of view, where density is maybe something that you think is kind of a big thing, and in measure theory, where you actually take the measure, like in this case, in the Lebesgue measure, you get that set is 0, where alpha is irrational. It just depends on your point of view, on how you want to take this. Okay, any questions on this?
do we say that it is almost periodic?
What's that?
It gets arbitrarily close to any point.
Yeah, I don't want to use the word almost periodic because it kind of gets close to eventual periodic, like it kind of sounds like that. You could, with the periodic points being dense in there, you can kind of, the density kind of tells you that the point is almost periodic in the sense that there's a periodic point arbitrarily close to it, right? All right, so looks like I'm running out of time for today. So the next time we'll talk about the doubling map and how to shift, the way that you can shift, can really describe your periodic behavior really easily, and how you can build periodic points just using shifts. I'll talk a little bit about how to compare to dynamical systems and talk a little bit about symbolics next time. Okay? And the symbolic dynamics deals with sequences. When can you maybe break down your dynamical system and code it into a sequence, and then use the sequence and maybe the shifting, there's a map called the shift map, to tell you something about the dynamical system. Okay. Right. Any last questions? Okay.
Happy birthday.
Thank you.